Now we shall talk about DeMorgan's law. Okay, so let's talk about it. Now there are two sets, A and B. Okay, and they are subset of X. Let's say it's given that they are subsets of X. Then we can represent this with the help of a diagram. So this is A, and this is B. This is X. So this is A, and this is B. Okay, and we can so A is also a subset of X, and B is also a subset of X. Okay, then De Morgan's law says that A union B prime, that is actually equals to A intersection A complement intersection B complement. Okay, so complement of A union B is defined as complement of A intersection complement of B. So now we shall prove De Morgan's law, and it is very obvious and it is very easy to prove. So let's give a try and let's prove it. So this is our set. Okay, this is our set, that is A union B complement. So A union B complement, which means that we are so let's choose an element X. Let's imagine that there is an element X in our required set. Okay, so let's imagine that there is an element X that is present in this set. So if, and this is actually the shaded region, which is a subset of this larger set X. So we can say that X belongs to X, and we can also see that X does not belong to A and B. Okay, if X is an element of A union B complement, which is this shaded region, then X is a subset of X, this capital set, this larger set X, and X is not a part of A and B. It is very obvious. So from here we can write that X belongs to X and X does not belong to A. Okay, and X belongs to X and X does not belong to B. Okay, using these two statements we can write that this is actually X belongs to A complement. What does it mean? X is an element that is not part of A but that is part of X. So we can define that X is A complement. Here we can understand it. X does not belong to A but belongs to X, so it is A complement. From these two statements we can conclude that X belongs to B complement, and because they are connected by logical connective AND, so we can and as we learned that AND is actually equivalent of saying intersection, so we can say that X belongs to A complement intersection B complement. So that's how we can prove De Morgan's law. I think it is quite easy. So that's about De Morgan's law. It is very convenient to use these Venn diagrams because they talk more than statements. So I'll recommend you to use Venn diagram while solving problems. That's very easy, and you can prove all sorts of things by using this very basic principle of proof that's available to you. Okay, now let's talk about cardinality of sets. So let's talk about that. Now let's talk about cardinality of a set. So cardinality is nothing but order. So it is order, and we learned what order is. So it is order of a set. Okay, and order means a number of element in a set. So this is cardinality. Cardinality means, and it is represented by this symbol, and I mean, I don't think we need any symbol, but this is represented. So there is set A, which is 1, 2 and 3. Okay, then cardinality is represented by this modulus sign, or it is also represented by this small n preceding this braces, which is A as an element inside, and it is also represented by this. Okay, this hashtag and with A. So cardinality of A is 3 because there are 3 elements. So I think we should not talk more about it because it is very obvious. So that's about cardinality. Now there are few theorems about cardinality of a set. I mean, that is, you can replace the word cardinality always with the word order. So cardinality is always replaceable by the word order to have a better and a very common understanding. But cardinality is generally the most suitable word used in the books. Okay, so there are some theorems about cardinality. So if A and B are two finite sets, then A union B, which means that cardinality of A union B, which means that number of elements in A union B equals to number of elements in A plus number of elements in B minus number of elements in common part of A and B, that is intersection of A and B. Okay, so now let's prove it with the help of our Venn diagram. We can prove it by use of simple DeMorgan's law and by use of a little bit of set manipulations, but we shall prefer obviously Venn diagram. So just let's prove it. So this is set A and this is set B. Okay, so this is a common region that is defined as A intersection B. Okay, so that's a common region. Now when we are counting elements, number of elements in A union B, that is cardinality of A union B, we are counting this A, we are counting, so we counted this intersection once, and while counting B we counted this intersection twice. Therefore we counted A plus we counted B, but instead of counting this intersection once we counted it twice, therefore we have to subtract it once. Okay, and that's why we have to subtract this. So I think this is very easy proof. Now we'll generalize this. Now we will find cardinality of 3 sets. Okay, and now let's talk about that, how fundamental it is, and then we'll do some problems on it. Okay, now let's talk about cardinality of 3 sets. Now let's talk about cardinality of 3 sets. So if A, B and C are 3 finite sets, then a cardinality of A union B union C equals to cardinality of A plus cardinality of B plus cardinality of C minus cardinality of A intersection B minus cardinality of B intersection C minus cardinality of A intersection C plus cardinality of A intersection B intersection C. Now this is kind of a this is kind of a poetry I'm reciting to you, but now let's prove it. We can actually prove it. So to reduce our effort, I'm just taking that A union B as X. Okay, I'm just assuming that A union B is X. Therefore cardinality of X technically is equals to cardinality of A union B. Now I just assumed A union B as X, so to reduce our effort, instead of writing always A union B, I'll just write X. Okay, so A union B, cardinality of X, which means the number of elements in X will be number of element in A union B, which will be, as we learnt in our previous theorem, that it is number of elements in A plus number of elements in B plus minus number of elements in A intersection B. Okay, so that's, now let's prove it. Then it says that X union C. Now X is A union B, so it is actually this. So this is actually the same thing. This is what you do for it, and this is, so X union C would be, using our last theorem which we learned, we can open this as cardinality of X union C is cardinality of X plus cardinality of C minus cardinality of X intersection C. Okay, now cardinality of X is cardinality of A union B. Okay, plus cardinality of C minus, now again we can write X as A union B intersection C. Okay, now again cardinality of A union B is cardinality of A plus cardinality of B minus cardinality of A intersection B plus cardinality of C, and we can open this bracket by using property of sets. So I'm just writing it like this. So this is cardinality of A intersection C union cardinality of B intersection C. Now we can again think this as P and this is Q, so it is actually written as cardinality of P union Q, and we know what is cardinality of P union Q. It is cardinality of P plus cardinality of Q minus cardinality of P intersection Q. Okay, so we'll just replace P and Q with our actual terms, so we can write this as negative times of cardinality of A intersection C minus cardinality of it will be actually in brackets, so this is cardinality of B intersection C minus cardinality of, let me just write it more clear, this is cardinality of A intersection C plus cardinality of B intersection C minus cardinality of A intersection B intersection C. Okay, and we can keep writing these terms. This is minus actually, so this will be minus. This is cardinality of A plus cardinality of B. So now we can see that we have actually proved this. So we have actually proved this, so it is equals to cardinality of A plus cardinality of B. Now I am just rearranging or writing it more beautifully. So this is cardinality of A intersection B minus cardinality of B intersection C minus cardinality of A intersection C, and this minus will be a plus, so cardinality of A intersection B intersection C. Okay, I think we have proved it. So by the same means we will prove the cardinality of n sets and see what we are getting, and we will generalize this formula. Okay, so I think that's how we prove, and now we shall prove for n sets. Now let there are n finite sets, so set a1 a2 and a3 dot an are n finite sets. Then we are being asked that what is cardinality of a1 union a2 union dot union an, and by previous two examples we can actually write this out. So this will be summation of cardinality of this minus this will be cardinality of intersection of two consecutive sets in order. This is cardinality of two consecutive two sets taken at a time. Then there will be a plus with one, we can say I, and then we define j and then k, and then there will be cardinality of three sets taken at a time, so I, aj and ak. Okay, and then we can define for, and again there will be minus, and there will be I, j, k and else, and we'll take four sets at a time. So, and that's how we define it. So we don't need to write all the terms, but that's how we can gently give alternate plus minus, and we can increase with ij, and we added a k. In next we will add it kl, and we'll take four sets at a time with minus, then it will be a plus, and we'll take klm, and we'll take five sets at a time. So that's how we define cardinality of n sets. I think it is very basic. So that's all for today. So like, share and subscribe. Thank you.